as we get into Chapter 11 with hypothesis testing or significance tests for means, today we focus on the one sample material. And so when working with proportions, we use the z-test since they are based from z values from a normal distribution. When working with population mean, we use a t-test. From a t distribution with the n-1 degrees of freedom. We worked on the n-1 degrees of freedom in the confidence interval section we did over the last couple days. To keep it straight, there's a little nickname thing here. We got the ZAPTAX z-test for proportions and a t-test for means. Now, I will say this. We're going to focus on z-test for proportions and a t-test for means. If I do me a favor, I'm just going to pull up the graphing calculator real quick. And I do want to show you something here where you can, we're not going to do it for our course, but you can in other courses or in life as you're doing these statistics things. If I go over to test, we'll notice there is a z-test. And notice after that z-test, it does not say, it doesn't say proportions on it at all. That z-test is technically a hypothesis test for z, but you can only use it when your sample size, or you should only use it when your sample size is bigger than 30. Okay, it is when you should use that one. All right, and then before when I was teaching this class the first couple of years, as I was learning how to go on the fly teaching the stats, I had my kids pay attention to 30, and if it was 30 or more, they used the z-test or a z-interval for means. And then we started, some of them were having trouble balancing when do I use what. So then we just, and the course kind of recommends too, is say, hey, let's stop. Anything with means, we do a T type of thing with it, whether it's a T interval or a T test. Anything that deals with proportions, you do it with a Z. Just to make it simple. You got two procedures. Not one of the things means has actually two options. We took away one of the options. And it seemed to make things a little bit easier on people's brains. Because as you think about our pictures from confidence intervals, on the first day of confidence intervals, it talked about that as my sample size, as n gets bigger, to 30 and more, I start resembling a z distribution. I start resembling normal. That's what that little table B did as well. As we went from degrees of freedom of 2 all the way down to infinity, we got closer to what those z numbers were. Okay, so. And that's where, you're not wrong for using a z-test when you're dealing with 30 or 40 or whatever. You just may be off a little bit on the numbers, not significantly off. You still make the same decisions and stuff that was taking place. So, but again, our course mainly for the AP test focuses on, hey, let's do proportions with a z, and then anything means related with a t. That way, I just got one or two options to work with. Okay. But some of your other later courses in life, some of your professors may have you do a Z for means. And again, you can only do that as if you're 30 or bigger. So just to share that with you, that's just a little small sidebar. Conditions for population means using a T distribution. One, again, we got to be a random sample or a randomized experiment is what's got to take place here. Now, here's where our normal condition is a little bit different. Notice how it's not just here. We have some options when we are less than 30. If your sample size is less than 15, we can use a T procedure if the data appears close to normal. So when I do a normal the normal distribution line, when I do that normal probability plot, if it is skewed or has outliers, we don't use the T procedures. That means we stop. We don't do it, okay? If our sample size is at least 15, so that's the 15 to 30, so 15 to 29, let's say, T procedures can be used except if the data has outliers or strong skewness. If it has slight skewness, it's okay. Strong skewness is a no-no. Again, when we have large samples, sizes 30 and bigger, T procedures can be used even for clearly skewed distributions and so forth. So we don't care about it when you have a sample size bigger than 30, what the population looks like if it's skewed or normal. We're going to be anything bigger than 30 means we're going to be going approximately normal in general. We still have our same independent clause. 10 times little n, is it less than or equal to the population size? When we write our null hypothesis, we are assuming that the null hypothesis is true, is what we're assuming. And then the test statistic is how far away n differs from the parameter. So we have a t statistic in this part here, as opposed to a z-stat when we did hypothesis testing for proportions. Due to our t distribution, our test statistics, well, this is what the generic formula looks like for this part here. Our t statistic, our t stat, is equal to our x bar minus mu naught. So the mean, the hypothesis, null hypothesis value in that over s sub x divided by the square root of n. So that's our test statistic. Now again, we have options as we're doing all these things in these in the hypothesis testing. We have options to use. We use the normal CDF when we were doing proportions, so we use the z statistic as one of our upper or lower bounds, and we did that. If you notice on my page, I haven't scrolled up far enough, but you can see it on yours. It's actually at the very bottom crease of my screen here. We have what's known as a TCDF. All right, and a TCDF is for a t distribution. The nice thing about a TCDF is it allows you to adjust the upper and lower bounds and that kind of stuff. So it does, But again, if you don't want to use that process, I'll show you how to do the t-test in the TI-84. So once we have calculated our test statistics, we can use table B to find our p-value, or we can use the calculator. Okay, we can use that one as well. Using the calculator to compute the p-value, we have two options again, using a t-distribution, which is this TCDF. You have to type in a lower bound, an upper bound, and then you got to type in the degrees of freedom. And that's all you have to type in on that one. So if you choose to do, hey, let me do it by hand, get my t statistic, get that number, then let me go in there and let me do a TCDF to figure out the p-value, the probability of this thing occurring, then I can compare it to the alpha that we're doing. And we're still dealing with the 1%, 5%, and 10% alphas as we're working with these topics with hypothesis testing. Again, if it's not stated, what number are we supposed to use? What type of alpha if they don't state it? 5%, thank you. Okay. All right, so again, our little 4-step process, we want to, what hypotheses do you wish to test and at what significance level? So our generic statement here is we're going to test the hypothesis that the true mean and then whatever the variable is, the context of the variable, and then we talk about at what significance level. We write our HO and our HA statement is what we write. Our HO is going to be that our mean is equal to the null mean that they put in the problem. And then our HA statement, we choose one of the inequalities based on the context of the problem that they're asking, paying attention to the inequality verbiage that they use. When we go down in the plan stage, we got to name the procedure, which is this first one right here. Again, this is where I need us to get a little bit better at when you do these things for me for a test. You need to write that. Hey, we're going to do a one-sample t-test for means. All right. Now that we have means and we have proportions, we need to make sure we just can't say t-test to assume that they know what they are. Because I've seen kids write t-interval for a hypothesis test. So they're going to nitpick for that point. Are you saying the right stuff? Okay. Random conditions, we're doing the same thing. Is it a random sample, a random assignment, or a random experiment? Is where that's associated with that last part. Then we get to do the check for normal based on those three conditions we went through just a moment ago. Check independence for the 10% rule. And then we go through and calculate. If you're doing it by a TCDF, you're going to calculate what X bar is, what S of X is. Find out what your degrees of freedom, and we kind of just work through that whole problem there and stuff. So, you know, which we'll practice doing it that way. We'll also practice it doing, we'll practice doing it with the faster method. As we look at setting up our TCDF, what's your upper and lower bound? Again, it's all based off of what your inequality you're using. If you're using that your HA is greater, then you should be having your upper bound be 100 and your test statistic is the lower bound. If your HA is less than, then it's your lower bound's negative 100. Your upper bound is the test statistic. If you're using the not equal to sign, then you can use either one of the above. Doesn't matter. Just make sure you multiply your TCDF by 2 is what you got to make sure you do. Because remember, when it's a not equal to, that means there's 2 areas that are shaded is what that means. Then we go through our little test here, and we can go through the process. So as I look at this first example here after the conclusion, I look at this first example and I see that, okay, they have stuff listed for me to find the data. They give me a bunch of data, and which means I need to figure out what is X bar, what is S sub X is what I need to go through to do when they do this. So I'm going to go ahead and split my screen here, and let's get a calculator going here. And I'm going to go stat. I'm going to go to edit, and I'm going to type in those numbers. All right, so I think I missed one. 27, 33, 32, 21, 30, 30, 29. My 25 and 27 were on the same line. That's why. 27 and 34 was the last one. All right, that looks good. All right, so I'm going to go in here and do stat, 1 var stat on L1. Again, I'm going to do this one the long way in case you forget the faster way. 28.8. S sub X, I'm going to grab it out to 6 decimals. 3.938415. That means, and again, I went out that far because I know that's going to keep me accurate for what I'm doing. So I went ahead and grabbed that information. And then now I'm going to go ahead and grab my, let's see, what do I want to do next? I do need a test statistic. I do need a T-star here. So I'm going to do that real quickly here. Hold off. I'll do that one later on when I need to. All right, so I got that stuff real quick. Can we conclude that the average speed of drivers in the construction zone is greater than the posted 25 miles per hour speed limit? So when we look at our HO statement, our mean is 25 miles per hour. Our HA statement, is it greater than? Is the average speed greater? So is it greater than 25 miles per hour? And then again, we got to define what mu is in the context of the problem. We got to say that mu is the true mean speed of the drivers in the construction zone. Again, it's the true mean speed of the drivers in the construction zone. I'm going to scooch that up a little bit. Now, what are we going to do? We will perform a 1 sample t-test for means if conditions are met. All right, let's see. They told us in the problem, random sample of 10 drivers. So fantastic. We got a random sample of 10 drivers. Normal. 10 is less than 30. So graph. All right, so we got to go through and graph, which means I'm going to do that normal probability plot. I got to graph that sucker. And again, I'm looking for outliers, strong skewness. If it is, I'm not going to do it. So I'm going to go ahead and split my screen, get back to my calculator. I'm going to go up to my stat plot, so second y equals. I'm going to turn plot 1 on. And then when I go down to the type, we're going to go to the very last graph. All right, again, I'm pausing there to make sure in case I'm going too fast. We used that one before, okay? So that's the last one to help me show, hey, that I use for normality. So I'm going to hit enter. And all my data is in L1. And the rest of that looks good, so I'm going to hit graph. I won't see it because I'm dealing with stuff above 10, so I'm going to hit zoom 9 for zoom stat. And then I'm going to quickly try to graph this. All right, so this is not bad. It's pretty linear. All right, so I don't see any distinct crazy curving going on to where I'm thinking it's not normal in that sense. I do have a little bit of, we're going to be on guard for, hey, is there an outlier there? Is that an outlier? Now, how can I check if there's an outlier? If I really want to be picky, how can I test to see if that bottom left value, is that an outlier? What can I do? Then, Gene, you're right. It's doing that IQR rule to multiply 1.5 times the IQR, and then I can test that value. Okay, so if we had to be picky and say, hey, that there is a good diagonal gap there, which means that could be a potential outlier. If I really wanted to go through and do it, then I would go through, calculate the IQR. Remember, do a 1-bar stat. It's going to be on there. Find it, and then subtract from Q1 what 1.5 times the IQR is, and then I can see, is that data value the smallest one? Is it too far out? If it's outside the fence on the lower side, then it's an outlier, which means that we probably shouldn't do this because we are less than 15. All right, now we're going to assume that that's okay, so we can go ahead and keep going. But but that's one thing I would think about in the real world of going through and checking that to be sure. So we're going to say that's okay. Independent. 10 times 10 is 100. So again, on this one, I would say here, and this is where, if you think about it, does one driver's speed affect another in a construction zone? Does somebody driving in a construction zone, does their speed affect somebody else's? Yeah. So we got to say, okay, that may not be the reason why I say they're independent. Are there more than 100 people that go through a construction zone? Yeah. So on the first one, we know it's possible that one person's speed could affect another person's speed. So we're just going to say, hey, it's reasonable to assume more than 100 people or cars, whatever you want to say, go through construction zone. Again, they don't tell us what time of day it is. They don't tell us, what time of day it is. I mean, because we know certain times of day, there may be very little traffic, so you can fly through the construction zone and your speed's not impeded. There's other times during rush hours when it's going to be backed up and it's going to be impeded. So, it kind of along that line. So now, our due stage. We do have, again, as I shrink in here, grab my numbers here again, my X bar, I said was 28.8. My S sub X is equal to 3.938415. Okay. And so I need to calculate what my T-stat is. My T-stat. So then that's that new formula. So it's X bar minus mu naught over S sub X over the square root of N. So my X bar would be 28.8 minus my mu naught is 25 over 3.938415 over the square root of 10. All right, so let's get our fancy calculator back out. And let's second quit. Let's go alpha x, 28.8 minus 25 over, I got another fraction on the bottom, 3.938415. On the bottom of that, I got to put the square root of 10. All right, that looks pretty darn good to do in one fell swoop, so I'm going to hit enter. And this gives me 3.0511. Or we can, that's technically fine enough. If you want to go out further, you can, 395. So now that I have my test statistic, we are going to do, as I shrink my screen so I can write my code here, we are going to do a TCDF. We are doing greater than, so that means my lower bound is my 3.0511395. My upper bound, something really big. And my degrees of freedom in this case would be 9 because they said we had a sample of 10 cars. And again, that's going to give me my p-value. That's what that's going to give me, my p-value, so then I can compare it to the alpha. Split screen back again. I just realized as I said that compared to alpha, what did I forget to write down in the beginning? In my hypothesis statement, what did I forget to say? Yeah, I forgot to say what significance level. So I need to go back up there and adjust it and say at 5% because they didn't specify, so we got to do it at the 5. So when you go into second VARs, we are doing option number 6, TCDF. And my lower bound is 3.0511395. My upper bound is something really big. You can technically stop at 100 like I put in our notes. Our degrees of freedom is 9. And then go down the paste. And I find out that my p-value is equal to 0.00688. Okay. Now I'm supposed to compare that 0.00688 to 0.05. Well, obviously that's less than. So we're going to go back here and we could say, since the p-value is less than 0.05, we reject the null hypothesis. There is convincing evidence to conclude that and then this is where we just take our statement from the top. The true mean speed of the drivers in the construction zone is more than 25 miles per hour. Now remember, I'd go back and rewatch those videos on the type 1 and type 2 errors that I posted for you guys. Given your conclusion from part A, what kind of mistake did we make? Could we have made a type 1 or a type 2 error? Since we rejected the null hypothesis, that means that if we did something wrong, we did a what error? Anybody remember? It's actually a type 1. Fail to reject is 2. Reject is a 1. Okay? It's been a while since we did it, so that's why I was saying make sure you go back, rewatch that little video and stuff and those things. So a type 1, again, since we rejected, a type 1 is associated with rejecting the null. So we decided the average speed is greater than 25 miles per hour when it really isn't. Now, so what's the mistake in context? Well, basically, we wasted. Sorry, there's an I in wasted. Wasted time. We wasted. We wasted time by doing this for us. It was a waste of time. And where is it a waste of time? Is because if we say that it's greater, if we say that people are driving through that construction zone faster, there's evidence to support that. What most likely are law enforcement going to do? Well, that or they're going to put somebody in by that construction zone so they can pull you over, right? And stuff. Otherwise, if they think it's, hey, there's not enough evidence, like, hey, we don't need to really put a cop car there and have somebody in there ready to pull people over for speeding. And so in this case, since we said, hey, there is evidence, well, what's the downfall if we were wrong? Well, we put a cop out there and we wasted time having them sitting there when actually people were driving the speed limit through that zone, and that cop could have been doing something else. Could have been somewhere else taking care of protecting us and doing other things, as opposed to sitting there just waiting for somebody to speed when we actually didn't have evidence of that being there. And so that's the consequence of a type 1 error in this situation. It's a waste of time for the cop. It's wasted time for a cop to be stationed by the zone, by the construction zone. Now, I'll be honest, and I'm sure you guys, as you guys are learning how to drive and are driving, it's very rarely in the almost 40 years that I have been driving that I have driven through a construction zone at the exact posted speed limit. And as you're driving, it's like your parents may have told you, hey, listen, you got to keep up with the flow of traffic. Whatever the flow of traffic is, that's what you got to keep up with. And that's what it's like when you're going through construction zones is, I will keep a safe distance between me and the person in front of me. I'll keep 2 to 3 cars at least in front. But I'll also speed up a smidge if I got somebody sitting within a foot of my back tire, of my bumper and stuff. And so, the construction zone's 25. I may try to do at most 30, but that's about it and stuff. And and I figure if I'm doing 5 over, and the person's on my gluteus maximus, then they deserve to pay all the court costs and all that other stuff if we get in an accident. And so I try not to sit on somebody's butt. I try to keep that cushion that way, I'm the one getting hit, which means they got to pay for everything, and I get to sue their butt. Is what gets to happen. So, Yo!
What does that word say
After who?
Oh,
that's a scratch out. It's like we wasted time. This word right here, this word right there. No, the orange. We decided the average speed is greater than 25 miles an hour when it really isn't. Sorry, my apostrophe turned into an I there too, and stuff. So, and my apostrophe got wild and stuff on that one. So, all right, here's another example again. Now let's do this one. Hey, we did put the alpha on this one. This one, let's do it a little bit faster. Instead of doing the T statistic, we're going to do this one with the what we call a T test. Show you the faster way to do it with the calculator. A college professor suspects that students at his school are getting less than 8 hours of sleep at night, which is pretty true. To test his belief, the professor asked a random sample of 28 students. How much sleep did they get last night? Here's the data in hours. Do these data provide a convincing evidence in support of professor's suspicion? Carry out the same test at an alpha of 5% level to help answer this question. So again, as we look at this, less than 8 hours, I'm going to underline that. I'm going to underline random sample so I can pick that stuff out real quick. So my mu is 8 hours. My ha, mu is less than 8 hours. Where mu is the true mean hours of sleep a college student gets. We will perform a one sample T interval T test for means if conditions are met. I tried to fill in some of this stuff for you to make it go a little bit quicker. We did a simple random sample of 28 students. What does the normal probability plot show? All right, so again, we are 28, which is less than 30, so we're supposed to go through and graph this. Even though we're so stinking close, we still got to go through on the AP test, and we got to type all that data in and see what does that normal probability plot show us. So Coach Stevens is going to clear out table 1 there, and then he's going to shut up and start typing in numbers. Oh. Who the heck get 9 hours of sleep? Oh, there's an 11. What the heck? Yeah.
It definitely will.
Oh, I doubled up there. Let me put a 3. I have a 63. All right. I got them in there. Not all in the right order, but who cares? That's all right. All right, so now second y equals. My plot's turned on. Sweet. I can just go ahead and hit graph. Hit zoom stat. Zoom 9. Ooh. Now, so you look at my plot. And so now some of you are looking at me like, Mr. Stevens, what? Well, now I'm going to go look and say, okay, did I have happy fingers? As I look at that, you know what I mean? I mean, before I say, hey, that thing's skewed, we got an outlier, I'm going to go see, okay, where did my happy fingers go? Because one, I got to change it. Otherwise, when I do the statistical stuff, it's going to be really messed up. So I need to go back in there and figure out, 96, the very first thing. So let's make that a 9. That means I got to, that sucks. I can put 6 at the end. Here we go. You what?
When I graphed mine looked pretty normal, and then the graph yours and it didn't look normal, so I was like, okay, maybe I screwed up something with the note, and I did, so I set it all back to 10. I was like, 20.
Okay. All right, so now second, I'm going to hit graph. It's a lot better looking. That's a lot better looking. So again, there we go. We look normal. Look normal here. All right. No outliers. And again, we need to do it. Again, 28's really close to 30, and so we should be thinking, hey, we're close, we should be pretty normal, but we also have to check for outliers and stuff on there. So slight skewness would be okay when you're between 15 and 30. It's just we can't have strong skewness or an outlier is what we can't have. So, all right, let's see. Yo! ¿Qué pasa? That's what you're getting. Well, hers is not as steep as mine.
Well, mine's not either, but I'm assuming you didn't re-zoom, not zoom, not.
I didn't.
You did that. You didn't.
Oh, I didn't resume Zoom 9?
Yeah.
Okay, that's why. So mine's off. All right. So mine's a little bit steeper than you guys and girls. There you go. Is that better? So, all right, but still good enough to be able to say, hey, we're the same. So, all right. All right, so we got that one. Yeah, because right, it was all, you know. All right, so we got that. So we're going to push that to the side. Independent. Does one student sleeping affect another student sleeping? Technically, it could, but so I would say independent, there's more than 280 students. Okay. College students, I would go with that aspect is what I would use on that one. So now we're ready to go through and do what we want to do. So what we're going to do is we're going to do a t-test in the calculator. So if I get back calculator back up on the screen just to help speed us up things a little bit, I'm going to go stat over to tests, option number 2, and I'm going to hit enter. And I have all my stuff in the data, so I'm going to do a t-test, and my data is column L1, okay? And if you want to make a note up here, we're going to put L1 up there. I'm going to put that up next to the data. That way on the reading, the reader can see that, hey, I'm putting that stuff in for L1. So I did data for L1. My mean was 8. And then I am choosing that it is less than, so less than mu naught. Okay, so I'm trying to do less than. All right, so data 8, the middle graph, go down to calculate. There we go. So this tells me that my test statistic, my t-stat, is negative 3.625. Now we leave the negative on this one. We take it off when we're doing the T-stars and the Z-stars. But on a test statistic, if it's negative, it's got to be negative. Okay, so on a Z-stat or a T-stat, we got to leave the negative on there. And then grab that extra 6. My p-value is 0.00059 is my p-value. So then I'm going to compare that to 5%. All right, I know that is less than 5%, so I'm ready to write my conclusion stuff here. Since the p-value is less than 0.05, we reject the null hypothesis. There is convincing evidence to conclude that, going back to our little statement up here, the true mean hours of sleep college student gets is less than 8 hours. Convincing evidence to conclude that the true mean hours of sleep a college student gets at least at this school is less than 8 hours. I gotta re-erase over. That looked like whores. We gotta change that. Hours. All right. Now, sometimes we have the benefit of them giving our information from a set of data in a nice summary table. And so we have to go through and be able to create the test statistic from there, or do all the stuff that we need to do. And so that's why I have this one kind of built in here so we can practice. What if they don't give me all the data values? They went ahead and did the one var stat and all that junk, that one var stat for us. So what does some of those things up there mean? Okay, so here's our situation. Again, it's a two-sided test. So to me, I'm thinking about in the Haas statement, I'm using a not equal to symbol. In the Haas statement is what I'm going to be going through and doing here. So in the children's game, don't break the ice. Plastic cubes are squeezed into a small frame. I remember that game. Each child takes turns tapping out a cube of ice with a plastic hammer, hoping that the remaining cubes don't collapse. For the game to work correctly, the cubes must be big enough so that they hold each other in place in the plastic frame, but not so big that they are too difficult to tap out. The machine that produces the plastic ice cubes is designed to make cubes that are 29.5 millimeters wide. The machine that produces the plastic ice cubes is designed to make cubes that are 29.5 centimeters wide, but the actual width may vary a little. To make sure the machine is working well, the supervisor inspects a random sample of 50 cubes every hour and measures their width. The output summarizes the data from the sample taken for 1 hour. So a simple random sample of 50 of them had a mean of 29.48, an SE mean of 0.0136, a standard deviation of 0.935, and then minimum, max, all that other stuff listed there. Do these data give convincing evidence that the mean width produced this hour is not 29.5? So that not is letting us know that, hey, different. That's what that not is. It's different. So it's not less than or greater than. It's just not that. And so that lets us know we got to use the not equal to. So we're going to test the hypothesis that the true mean width of ice cubes is 29.5. So our Ho statement, mu is equal to 29.5. Our Ha statement is not equal to 29.5. We define what mu stands for. We will perform a one sample t-test for means. So as we go through our conditions, we had a simple random sample of 50 cubes. 50 is greater than 30, so approximately normal. And then when we think about it, 10 times 50 is 500. There's more than 500 cubes produced in an hour, so I meet all those things right there. Now, since we don't have the data to type in, I have now two options. I can still do the TCDF. I can still use the t-test. I just got to make sure I use statistics. So as I look at I have two options. I can do a TCDF to figure out my p-value, or I can do a t-test. So if I choose to do a TCDF, and again, I have to show you this, so again, just in case they ask for the, a quick way to do the test statistic. Our test statistic, our t-stat, our x bar is 29.4874 minus our hypothesized mean of 29.5 over our standard deviation is the 0.0935, over the square root of my sample size. Okay? Now that's one way you can find the t-stat. The other way, we can start off on the top the same way. The SE mean, that is technically the standard error, is what that is. That's that fraction part on the bottom. So we can actually just divide it by 0.0132. if we do on a calculator real quickly, just to show you, if I take, come on, calculator, catch up. If I take point, come on, 0.0935 and divide it by the square root of 50, I should get something pretty darn close to 0.0132. Okay? So to save time, when they give you this printout, you can actually just use the standard error mean as the whole denominator is what you can go through and do, just to point that out. So then now I can simplify that, and that gives me a negative 0.9545. And then I would go to a t-test, or I go to a TCDF. Now, since it's a not equal to, we need to do a 2 times a TCDF. Since it's a negative, I'm going to do negative 100, and then I'm going to go negative 0.9545, and my degrees of freedom is 49. That should give me a p-value. If I type it in exactly like that, it's going to give me a p-value of about 0.3445 is what it's going to give me. If I don't choose to do a TCDF, then I can use the t-test, and I have to use statistics. I have to use stats. Whoops, that's a S. A. Which means I have to put in what is X bar, what is my, I think my N. I try to leave some brain cells for not memorizing everything. T-test, choose stats. There you go. I got to put in my mu naught. So my mu naught is 29.5. My X bar, we said, was 29. That long decimal there. 29.4874. My S sub X was up on that paper. We had 0.0935. And I am choosing the not equal to. I'm choosing not equal to the null. So as I enter those in, 29.5, 29.4875, 0.0935, 50 is my sample size. That's what I forgot on that. N is equal to 50. Leave that part alone. Hit calculate. And voila. On this one, again, it tells me what my T-stat is negative 0.9453, which is pretty darn close to what we had. Our p-value is 0.3491. Again, close enough to what we had there. Remember, why is it different? It's different because of when I'm doing the calculator t-test, it is doing the fancy formula to get the degrees of freedom, is what it's doing. Whereas when we do it by hand and we do a 49, it's shortcutting it a little bit, is what it ends up doing. So with that in mind, either case we can make the same decision. Compared to 05, what are we? Yeah, we're greater. Our p-value is greater than 0.05. We fail to reject the null hypothesis. There is not convincing evidence to conclude that the average width of a cube is not 29.5. All right. Now, here's what we got to think about. What type error could I have made in this case? A type 2, right? Right. And so where I'm saying, hey, there's not evidence when actually there is. All right. Now, what by doing that, if I'm saying, if there is evidence that it's different, what would I would do as a company? If I did have evidence that it was different than 29.5, what would I do as a company? Would I just let it go? Because what's the issue? They're not going to be the right size. The game no longer functions, no longer works. So if I don't check this periodically, and so forth, and it's not that, then hey, I'm wasting a lot of material. I'm wasting a lot of cost. Okay, which decreases now my profit. And so that means if there is evidence, I want to get a technician out there to fix it, to make sure it gets recalibrated. Okay. Now, what's the mistake if on this case, since we failed to reject, and there is an issue? Well, then that means that again I have a big issue. So I guess a type 1 error, there is evidence. I get somebody out there to fix when I really didn't need them. Type 2 error is I didn't get somebody out there to fix it because I didn't think there was an issue, but there actually is an issue. So here a type 2 error is actually probably more severe because of the financial impact. It's cheaper for me to get somebody out there to tweak it and fix it as opposed to wasting a whole bunch of product. So here I would say here in this situation, a type 2 error is more severe because of the financial impact as a company and stuff where I just have a lot of wasted material and so forth, and so I'm decreasing my profit. And it depends on how long I let this go on. Now they're checking it every hour, which is great. They're trying to make sure that hey, if it does go bad, we fix it quick so we minimize the loss that we end up having. Okay, so that's that quality control part and stuff. Inspector number 12. You guys ever get that enclosed anymore, like in a pocket, where it says it was inspected by a little piece of paper said inspected by a certain person? They used to do that. They used to have, especially in clothing, they actually used to have a little piece of paper, like little cloth piece of paper, or something that actually was in like a pocket, and something, and it said it was inspected by, and it had somebody's number and stuff on there. Now I don't know what they do now. I don't know if they actually throw out the person. They don't have a person doing it. But it was always, it had a little. It used to be that way. Ask your parents. I'm sure they remember it because they're old like me and stuff. So, all right, 2 significance tests as we try to get through this part real quick here. Unfortunately, the significance test doesn't tell us the actual value of mu. For that, we need the confidence interval is what we need. The connection between significant tests and confidence intervals is even stronger for means than it was for proportions. That is because both the test statistic and the confidence interval use the standard error of X in the calculations. So when two-sided significant tests at a level of alpha rejects the confidence interval, for mu, it will not contain the hypothesized value. Remember that. And when the test fails to reject, the confidence interval will contain the hypothesized value. Okay, so that's a key thing as we look at sidebar questions where they'll say, hey, we did this hypothesis test. Here's our outcome. What would the confidence interval, would that number be in the confidence, would the hypothesis value be in the confidence interval or not? So on this thing right here, they said, another type of way we get data is through this Fathom software. Here's a 95% confidence interval for the true mean width of plastic ice cube produced this hour. Interpret the interval. Would you make the same conclusion with the confidence interval as you did with the significance test in the previous example? So here's my little interpretation, and then I'll answer the part there. So with this, in this mind here, I got to zoom in. We are 95% confident the interval. Let's see, where's our interval? They tell us, there's our interval right there. Our interval from 29.4609 to 29.514. contains the true mean width of an ice cube. And now the answer to the second part of that saying, would you make the same conclusion? Yes, we would make yes, we would make the same conclusion. Because 29.5 it falls in the interval. Falls in the interval. So that's part A's answer. Part B, they asked us to interpret the confidence level. If we took many samples of size 50, approximately 95% of these samples would capture the true mean width of an ice cube. All right, inference for means, and we got paired data. Comparative studies are more convincing than single samples investigations. Therefore, one sample inference is less common than comparative inferences. Study design that involve making two observations on the same individual or one observation on each of two similar individuals is the result is what we call paired data. This experiment design is called matched pairs. All right, so when we think about this, especially in the medical world, if I want to see how a drug affects men and women and so forth, one, ideally what I'd like to do, is to have the individual maybe go through the study twice, where it's like maybe once with the placebo or whatever we're doing, and then a second time with whatever's going on, and then I can compare the difference before and after. Sometimes when we're dealing with medicine like that, we can't. There are situations with certain things we could. So sometimes what we could do is, how many you have Mr. Edwards? Okay. He and I are about the same size, aren't we? Okay. We're about the same size. So we're about the same age too. Okay. So with that in mind, if I was trying to do some type of study on the effect of maybe a blood pressure medicine or something else on that line, then since he and I are about the same physical size, about the same age, then we could be paired up where maybe one of us randomly gets assigned the placebo and the other one gets assigned the drug. And then we can do the study and then compare the difference between the two. All right, that would be what we call matched pairs. All right. Again, there are some situations when we can put a person through the thing twice. I know you did this already, just because you're wearing your scrubs. So I'm sure you did this activity. I don't know if I did it with you and Gene back when you guys had me last year or not. On standing heart rate and sitting heart rate. Okay. Did I do that with you guys?
Yeah.
Oh, I did it with you already. Okay, so yeah. So there's an example with the standing and sitting heart rates where that's a matched pair. I forgot we did that back in chapter 4. We did that activity. I got you, sweetie. I'll get my glasses at the same time as I drop them. So yeah, so like that, when we did the standing and resting heart rate with you guys, that was an example of a matched pair. So there are certain situations where you can send an individual through both things. Sometimes you can't. And so that's where we try to match up individuals like Mr. Edwards and myself as we're doing things. You know, we don't want to match up Mr. Powell and myself. We are the same age, but we're two totally different sizes. One, he's like 8 inches taller than I am. Okay? I got my recording going, so I'm not going to say the other aspect of how we're different and stuff. So we don't have evidence and stuff. So, like my brother is a year younger than I am. He is. I mean, our birthdays are 15 days apart. So he's like, I'm a year and 12 days older than him, or 13 days older. Now the challenge with my brother, even though we're close in age, yeah, we have the same genetics. I weigh 235. My brother probably weighs about a $160 is what he ends up weighing. And we are a big difference in the weight part. So that may take some consideration as we're looking at a study on some type of medicine involving my brother and I, because, hey, there's a big difference in the weight. And so, you know, is that going to affect the outcome that could have come about by doing the true drug and the placebo? Okay? So that's where, you know, and, you know, again, if we could do it, then obviously that would be the best, you know, for my situation and his to do a best match pairs for something, because all the genetic parts are super close in what we're doing. So here's an example of doing one of those activities where they gave us some selected times. Now here, with this in mind, I know we're getting close to the last 10 minutes of class. So here's what, if we're just going to get into a whole bunch of copying down here. This is that part of the lesson earlier where we talked about the mu d sub d. We talked about a mu sub d, right? No, I guess I blew over that real quick on that last part there. All right, so the mean difference, mu sub d. So that's what then when we do a paired T procedures for matched pairs, and we're trying to find the difference, we try to find what mu sub d is. So they'll tell us like the difference here. So I have this kind of set up in my notes here where we're doing regular minus express. So they're trying to see, is there a difference between when I go through the store with using the regular lane and using the express lane, is there a difference? And so I went ahead and subtracted these. So if you just want to copy down the numbers, you don't have to do the calculator. 5, 246, negative 46, 121, 30. I meant to copy these down earlier for you, and I didn't. My bad. That's a 79, by the way. Negative 94. Negative 17, 95, 20, 14, 129, negative 39, and then 42. All right, so there is, and again, as I put over here as a little note, I didn't read the whole paragraph just because we're close on time. So if you're re-watching this video, just pause it and read it. We will consider the difference in time and we're doing regular minus express. So a positive value So what does a positive value mean? If I'm doing regular minus express, a positive value would mean that the regular is faster, correct? Or vice versa. If I have a positive value, if I'm doing 42 regular, 342 minus 337. I do have a note down here, but that's what sometimes when my brain gets my ADD, I think I have the note down here that positive value means the express was faster. Which is what you were saying, kind of. My ADD kicked in and I got distracted from the problem there, so I lost my good train of mathematical thought, statistical thought. So, all right. Now, all we want to do is we want to put just these orange numbers into L1 is all we want to do there. And so as we look at our statement here, we will test the hypothesis. Notice how I left this one totally blank, like nothing pre-filled in for you. We will test the hypothesis that the express lane and the regular lane are the same. Remember, in the null hypothesis, we're saying, hey, there is no difference. So this tells me that for my host statement, that mu sub regular is equal to mu sub express. And we're going to do it at the same speed at an alpha equal to 0.05. So I went ahead and stuck in that 0.05 there real quick above the little squiggly line there. Now, what is my Haas statement? And now, so the way I have that written, that it is actually, I have it written like a 2 sample because we're only doing 1. Let's tweak that. Let's tweak that. So we're talking about mu d. So mu d is equal to basically regular minus express. So that mu d is equal to 0. My Haas statement is that the mean is positive. Mu d is positive. It's greater than 0. And then I would want to specify what mu d is. Mu d, and I know the bell's going to ring in about 3 minutes. Mu d is equal to the actual mean difference in times of regular minus express required to purchase an item at this store. And so and here's where the little difference is when we talk about our plan, we're going to actually state here, we will perform a paired t-test. So that's actually what we're doing. We're doing a paired t-test if conditions are met. And so for random, I didn't leave enough room here. Random, they did tell us if we go back and reread it, they went through, they did randomly selected 15 times during a week. They went to the same store, bought the same item, and then they also did random. One of them used an express lane, one used a regular lane, and they would flip a coin. So they did random assignment for time of day, random time of day, and lane assignment. So they were trying to be really careful on that. So what I'll do is, this is probably a good place to stop here. We'll finish up the rest of this tomorrow we'll do a quick little part 2 video of this, and then we'll do we'll get into the next lesson.